So now we turn to the question of what it means when a system exchanges energy with its surroundings. And the answer to that question constitutes the first law of thermodynamics. And the first law of thermodynamics is disarmingly simple. It says that heat and work are the only means by which a system exchanges energy with its surroundings. That's remarkable. It's that simple that the only way to change the internal energy of a system is through heat or work. So let's take a look at this equation. We're going to look at the change in internal energy of the system, and the first law states that the only way to change that internal energy is through the addition or extraction of heat, or by doing work on or having the system do work on the surroundings. So work and heat. The first law says that's the only way you can change the internal energy. And then we step back and we look at the logic of this, because heat is microscopic energy and work is macroscopic energy. So another way of formulating the first law of thermodynamics is to say the only way to change the internal energy of a system is through the addition or removal of microscopic energy, or by the addition or removal of macroscopic energy. And so you say, well, all right, logically, energy is either microscopic or macroscopic, so that has to be the case. But look at one more aspect, and that is that I can draw this barrier right down through that equal sign, and on the left-hand side is the system, and on the right-hand side are the surroundings. And as we'll see when we solve any problem in thermodynamics, the first thing we do is write down the first law of thermodynamics, because it clarifies things in a remarkable way. So let's take a quick look at what heat and work actually mean. So let's suppose I have a body, a block of steel, for example, and the block of steel has a temperature of T1, and I move it up against a block of steel that has temperature T2, but T1 is greater than T2. That is, the block on the left has a higher temperature than the block on the right. And if that's the case, heat flows from the high temperature body to the low temperature body. That's an example of microscopic energy transfer. So we see already that heat is actually a dynamic transition of energy across a border transferred by molecular motion, because only then is it heat. So let's take a look at the work side of this. We know from both chapter 1 and 2 that work is equal to a force times a distance. Newton was the person who worked this out, and it was a critical part in the development of the conservation of energy. But now let's take a look at what this means to chemistry, because if I start out and I have reactants A plus B going to products C plus D, and gas is given off by that chemical reaction, and I have a fixed pressure on the top of this piston, and a fixed pressure, say 1 atmosphere, on the top of this piston, then the evolution of that gas actually moves the piston up a distance delta x. So how do I calculate the work for a particular example that I have here? Well, the force times the distance, I can write the force divided by the area of that piston. So I've got an area of the piston that is equal to A. So I divide the force by the area. Then I have to multiply the area back to maintain the equality. And then I have a distance d, but that distance of displacement d is equal to delta x. Okay, well now I step back and I look at that equation, and I recognize that the force divided by the area is just the pressure, the downward pressure on that piston. And that means that I have the pressure times the area times delta x. Well, that's interesting because if I multiply the area of the piston times delta x, that's equal to the volume of the displacement. So I can write that as A times delta x is equal to V. But then I come back to my sign convention, and I realize that that piston is moving upward, and it represents work done by the system on the surroundings. So I have to remember to put that minus sign into the final representation of what that work is to agree with the convention that we've just worked through. So that work term is equal to minus pressure times the volume. And so that is the macroscopic component of the energy exchange between the system and the surroundings. So now we have an evolving picture of what it means to transfer energy microscopically, which is the definition of heat, and how we transfer energy macroscopically, which is the definition of work.